let's solve another Leetcode problem today. So today's problem is to delete duplicate folders in system. So due to a bug, there are many duplicate folders in a file system. You're given a 2D array path where paths of I is an array representing an absolute path to the ith folder in the file system. So this path represents this path. Two folders not necessarily on the same level are identical if they contain the same non-empty set of identical subfolders and underlying subfolder substructure. The folders do not need to be at the root level to be identical. If two or more folders are identical, then mark the folders as well as the subfolders. Okay, so this is saying that slash A and slash B are identical because they have the same internal subfolders, right? Both have slash x, both have slash x slash y, and both have slash z. However, if the file structure also included the path slash b slash w, then the folders would not be identical, right? Note that slash a slash x and slash b slash x would still be considered identical even with the added folder. That's because they both will still have y, so they both are identical. Once all the identical folders and the subfolders have been marked, the file system will delete all of them. The file system only runs the deletion once, so any folders that become identical after the initial deletion are not deleted. Return the 2D array answer containing the paths of the remaining folders after deleting all the marked folders. The paths may be returned in any order. So in order to solve this problem, try to see what the approach will be. So let's just take this test case. So what we'll do is first we will see that these are folder structures, right? So these are hierarchical in nature, right? So we can use a tree to populate the whole folder structure. So we'll do populate a tree. Then what we'll do is we'll try to keep a count of all subtree structures that we see. And what we'll do is basically we'll serialize a subtree and find a string form of every subtree basically. Don't worry if this looks very daunting right now, but we'll try to explore this visually so that this is understood. So, and the last thing we'll do is wherever count is more than one, right? That means that it is a duplicate and we can skip all such subtrees and populate the result array. Something like that. So let's take this test case of it has A, C, D, A, B, C, B, and D, right? So let's try to draw this, right? So in the tree that we'll populate, the tree would look like something like this. It will have A, C, and a D, right? And let's mark that with a dot to indicate that these are all leaf nodes because we have ACD, then AB, CB, and D, right? So let's draw the whole structure. How would the tree look like? So this will only have a B, and this is a leaf node. This will only have a B, and this is again a leaf node. This will have a, and this is again a leaf node, right? Then what we'll do is we'll traverse this tree. We come to this node, then we try to loop through all its children, right? So then we come to this node, right? It is a leaf node, right? So it doesn't have any more children, right? So when we go to its we when we try to traverse this node, the subtree structure below this is an empty string because it doesn't have any more children, right? So its structure we'll represent it in this form, an empty subtree below it and a B, right? And we'll keep a count of all the structures that we keep on seeing. This will have a count of what? 1. Then we go to C, right? C again the structure is the same, so we cut this and instead increment it to 2. We have seen this twice. Then we go to D, and this has a structure of something like this, right? Then what is the structure? We have four nodes in total, right? So what is the structure of this node? So in order to do that, we'll just use the structure of its children. So it will look, and we basically use the structures in lexicographical order, so that like even if the folders are given in some random order, we still get the same structure if they actually have the same structure. So what I'm trying to say is its string representation will something look something like this. A B C B, and last I think there will be a D A. And since we have seen this once, let's keep a count, and let's also map each node to its representation. So we'll keep a dictionary, but this map will be not mapped to this so that we can find its string form very quickly. Just look up this. This will something like this, right? Or not this, right? This will be mapped to this node. This is the subtree. Or sorry. Yeah. My bad. And this will be mapped to A. And yes, so once we have made all these mappings, right, we again do a DFS traversal and try to find all the structures where the count is more than 1, right? So first we come to this node. Then we see A has a child, so we go to this node. Then what we see is its ID is B, which we can quickly find through the lookup that I mentioned, right? But B's count is more than 1, which it is 2, right? So there's no point going considering this or going below, right? So we can skip this. Then we go to C. C has a child, right? So we come here. Again, we get the same result that B, this structure is already seen. So we come back again. Then we process this child. This has a structure of A, this, and it is a count of 1 only. So in the result area, what we can do is this will something look like something like DA, right? We append this because this is a count of 1. But this was also a child, so we just have to include this as well. We just have to keep in mind, right? And this will happen because we'll do a DFS traversal on this node, right? And this will first process the children and then process this as well. So basically that's a general idea, but let's try to code this approach up. So in order to code this, let's first define a class of tree node, right? And we'll have a constructor, and we'll say self dot children normal, however you define tree, try, whatever it is pronounced as. It will be defined as this, self dot path, and we'll just mark path for all the leaf nodes only, right? So let's have a root as tree node. Then let's populate this, right? Let's populate this tree, right? So what we'll do is for path and paths, let's start at the root, and let's say for folder in path if not of folder in node dot children, because it's a dictionary, right? So we can just add it. Node dot children folder is equals to a new tree node, and we can do node equals to node dot children folder, something like this, right? And once we have done this for loop, we'll say node dot path is equals to path, right? Once we have done this, let's have a default dict which will have to import dict, right? Something like this. So what we'll do is we'll define a serialize function. Let's let it take a node. So if node dot children are empty, right, there's nothing there, then we can just return an empty string, right? And child serials, let's define this as an empty array and then process all the children. So for all the child in sorted of node dot children dot keys, right? What we'll do is we'll call serialize. Let's copy this just in case we make a typo on child, and let's child serial value is equals to this, right? Not this actually, child, something like this. And once we have that, we'll just append this to child serials. Let's use an f string here, so it would look something like child, and then this, and then sorry, my bad. This will be child only, my bad. And child's basically this value, something like that, right? And once we have done this, the signature would look something like join this loop, this area, right? And once we have this, let's we didn't define it, so subtree count, let's define that as an default dict of int, right? And subtree map is equals to an empty dictionary. And what we'll do is we'll say subtree count of this signature plus equals to 1 and subtree map of node, and let's use the id function here to find the unique memory address, right, is equals to the signature, and we can return signature, right, something like this. And let's call this serialize function on root, and let's see how does this look like, whether it's being populated correctly or not, right. And let's return an empty just to satisfy the structure, just to be able to print, right. Default ticked, okay, my bad. Line 31. So as you can see, we have count of b is coming as 2, this subtree is seen once, and this looks correct, right. And we have all the mappings to the string forms, right. This is what we saw in the diagram. So what is left is just let's have a result and let's return that in the end. So what we'll do is we'll again do a DFS. So let's define a DFS function here, node. So what we'll do is let it have a result is equals to an empty array, and let's loop through all its children. So for name comma child in node dot children dot items, let's try to find the string so basically let's find the string form first. So str form is equals to uh, id of child, and we have this in the map, so sub map of this, right. And if we have this str form and sub of count of str form is greater than 1, right, then we can skip or basically continue this loop, right. And what we can do is do result dot extend dfs of child, I think, yeah, something like that. We can process subtrees under the children also, right. And yeah, we can say if node dot path is set, this means that it is the path and that it is a leaf node, so we can just append it here also, right. And return result, I guess. And before we okay, we are returning, so we don't even need this, we can just call this and return root. something like that. Okay, so let's try to see key error. One six. Okay, so we can just do a get here, something like this. I think we appended node by mistake. Yeah, I think this is running correctly now. So as you can see, the sample test cases are passing. So let's try submitting the solution now. As you can see, we have passed all the test cases. So thanks for watching.